Welcome back to AE 2220 Dynamics. In this video, we're going to start discussing non-rectangular components. So sometimes it is very useful to use non-rectangular coordinate systems. You may have seen things like cylindrical coordinate systems or polar in the past. We're going to consider two common systems here. The first is based on, I'll just say that the first is based on the path of the particle. First is based on the path of the particle, and the second is based on radial and angular displacements or polar coordinates. Let me rewrite particle. So the second is based on radial and angular displacements. And angular displacements. Or also polar coordinates. Okay, we're going to start off with the first one, of course, and that is called tangential and normal components. So recall that the velocity vector is tangent to the path, but the acceleration vector is not generally tangent to the path. However, we can decompose the acceleration into a normal and a tangential component. That is a component that is tangential to the path and a component that is normal to the path. We're going to go through and show that here. So if we consider a particle moving along a curve in a plane, here we've labeled our particle P, and we have a position at P and a position at P prime. We are going to then attach a unit vector, ET, and we're going to attach that to the particle at position P, and it's going to be tangent to the path in the direction of the motion. So tangent here, this is our E hat T unit vector. And then we're going to attach another one at a later point in time, or P prime. This is our E hat T prime. So it's a tangent vector attached to the particle at position P prime at some later time. So here these two unit vectors are attached to a moving reference frame. But we're going to go ahead and we're going to draw them from the same origin by attaching ourselves to that moving reference frame. When we are attached to the particle moving with that reference frame, from our view, E hat T is going to be fixed in place. Okay, so let's go ahead and let's draw our two unit vectors. First we have here, do it in the same color, so we have this E hat T, and then at that later time we have the E hat T prime. This allows us now to define the difference between these two unit vectors, which I'm going to draw here in purple. I'm going to zoom on in here. This difference, we're going to call this delta ET, and it's still a vector. In this case, it's not a unit vector, so it doesn't get a hat. It is just a regular vector, and there's some angle in here that we're going to call delta theta. Okay, so we can define this difference as delta ET, which is a vector, is equal to E hat T prime minus E hat T. And the angle between them again is this delta theta. So since ET and E hat T prime are both unit vectors, their tips are going to lie on the circle of radius 1. And that means that their magnitude is the same, and therefore the only difference is their angle or the direction they're pointing in. So we can then compute the magnitude of this difference, and it's going to be equivalent to 2 times the sine of delta theta divided by 2. And you can get this just from geometry. Let's now consider the vector delta ET divided by delta theta, and then take a limit as delta theta goes to 0. We'll find that this vector then becomes tangent to the unit circle, which means that it's then normal to ET. Moreover, its magnitude is going to become, we'll take that limit here, the limit delta theta goes to 0 of the magnitude 2 times the sine of delta theta over 2 divided by delta theta. This is going to be equal to, we can manipulate this 2 and bring it into the denominator, and we'll get that the limit of delta theta goes to 0 of the sine of delta theta over 2 divided by delta theta over 2. This is going to be equal to delta theta over 2 divided by delta theta over 2. It's going to be equal to 1. So thus we have now defined a new unit vector that is now normal to the tangential vector ET. So then what we'll find now is that this new vector, we're going to call it E hat n for the normal direction, is going to be equal to the limit as delta theta goes to 0 of the fraction delta ET over delta theta, and that is a vector, divided by delta theta, is equal to the derivative d E hat t over d theta, such that our normal direction E hat n is equal to the derivative of E hat t with respect to theta. And that is the definition of the normal vector for the normal and tangential components. Okay. With that, we are going to stop here, and we will continue when we get back to in-person class on January 13th. All right, thank you very much, and I look forward to meeting you in person.